Symmetries of Quadrilaterals, Unit 1, Transformations and Symmetry. In the Ready section, you have polygons, definitions, and names. Here we can use a search engine like Google and type in polygon definition. And we'll find that a polygon is a plane figure with at least 3 straight sides and angles, and typically 5 or more. A closed plane figure having 3 or more sides is called a polygon. A polygon is a closed shape with straight sides. The word polygon comes from the Greeks, like most terms in geometry, which they invented. It simply means many angles. A polygon is a closed plane figure bound by 3 or more line segments. We could continue to use search engines like Google to find the name of a polygon with 5 sides, and of course we would find that to be a pentagon. In the set, we have kites, lines of symmetry, and diagonals. So here we have a rectangle and a parallelogram, and we want to draw the lines of symmetry and find the centers and angles of rotational symmetry. So with the rectangle, there are 2 lines of symmetry. One horizontal line of symmetry that connects opposite midpoints, and one vertical line of symmetry that connects opposite midpoints. For rotational symmetry, for a rectangle, the center of rotation is the center of these perpendicular bisectors of the sides. We could also find the center of rotation by finding the intersection point of the diagonals. And rectangles have 180 degrees rotational symmetry, which means you can rotate the rectangle 180 degrees about the intersection of the diagonals, and the shape will be in the exact same position. For parallelogram, it does not have any lines of symmetry, but it does have the same rotational symmetry as the rectangle. If we find the intersection point of the diagonals, we'll find the center of rotation, and a parallelogram also has 180 degrees rotational symmetry. And what is a kite? A quadrilateral with 2 distinct pairs of adjacent congruent sides. Adjacent meaning that they are side by side, and they're congruent meaning they're the same length. So it has 1 pair and then a second pair. In the Go, you're justifying and matching transformations. So let's justify how you know that this shape has been reflected across the line y equals negative x. First, let's graph the line y equals negative x. This line has a slope of -1 and a y-intercept of 0, 0. Now let's think about reflections. Let's think about an easier problem. How would you reflect the figure over the given line x equals -1? I'd make sure the point that I'm graphing is the same distance away from the line of reflection as the original point. I'd do the same for both. So for reflection, remember the image and pre-image points must be equidistant to the line of reflection. So going back to our problem, are the image and pre-image points equidistant to the line of reflection? Let's check. We're going to find this distance by using the Pythagorean Theorem. So I'm going to draw triangles to my line of reflection, measure the distances so I can use the Pythagorean Theorem. I notice that these 2 triangles are the same size, so the hypotenuse for each triangle is the square root of 13, which means that these points are both square root of 13 units away from the line of reflection. So yes, these 2 points are equidistant from the line of reflection. Then I would of course need to check the other points. But we're not done yet. We also need to think back to Lesson 1, Leaping Lizards. What was the relationship between the line connecting the image and pre-image points and the line of reflection? The lines were perpendicular. When we draw line segments connecting the image and the pre-image points, we need to make sure that they're perpendicular to the line of reflection. How do we know if they're perpendicular? We need to check their slopes. These segments have a rise of 5 and a run of 5, meaning that their slope is 1. The slope of our line of reflection, remember, was -1. So yes, when we create segments connecting pre-image and image points, the line of reflection serves as the perpendicular bisector of those segments. And a perpendicular bisector cuts each segment into two equal pieces at a right angle.